everyone. This is the 23rd lecture in the Mathematical Methods for Economics series. We'll continue from where we left last time. In the previous lecture, which was the introductory lecture on differentiation, we had introduced the idea of a derivative as the principal mathematical tool for examining rates of change and slopes of curves. In particular, we defined a derivative in terms of an instantaneous rate of change as opposed to an average rate of change, which is something we'll talk about a little bit in today's lecture as well. So the plan of action for today's talk is as follows. We'll do a quick recap of what we did last time. And we will also explore the properties of continuity and differentiability and how they're related to each other. In particular, we look at the ramifications that differentiability has for continuity. In other words, we'll address the question, are all differentiable functions continuous? And we'll also turn the question around and ask if all continuous functions are necessarily differentiable. That is the first part, and we'll also examine some simple rules for differentiation. Simple rules, yet very important rules for the purpose of calculating derivatives. And finally, if time permits, we'll bring in the idea, I'll just introduce the idea of a proportional rate of change, which is quite relevant from the point of view of economics. So let me take a few minutes to just go over very briefly over the key concepts that we had covered in the previous lecture. And as I said, the derivative is the main mathematical tool for studying slopes of curves. So let's say we have this function here, which is represented by this curve in blue. I'm interested in knowing the slope. I want to calculate the slope of this curve at the point P. So a natural way to think about calculating the slope here is to draw a tangent, which is shown by this line L here. We draw a tangent at the point P, and then the slope of this tangent is taken to be as representing the slope of the curve at point P. So long story cut short, it is the slope of the tangent to the graph at P, which we call the derivative of the function at that point. Now what I'm going to do is, we're going to now, we'll try and conceptualize this concept of this tangent, because I have just thrown in this tangent and talked a little bit about how this tangent comes about in the previous lecture as well. So let me just quickly go through those slides. And here we're talking of the tangent in the following manner. So suppose you have this curve, which is just a part of curve that I'd taken in the previous slide. And let's suppose we consider this movement, which is from point P to point Q. Now, if I draw a straight line which cuts through the points P and Q, this is called a secant line. Okay, so what I'm going to do now is, now if you've understood the concept of a secant, basically I'm going to keep this point P fixed, and I'm going to get myself to move closer and closer to P. So instead of being at Q, I might move to a point like R, and if you look at the secant that you'll draw now, that will be cutting through the points P and R. So in this way, if we successively move closer and closer to P, which is the idea behind taking the derivative, we are taking very small, infinitesimally small changes in x. So as we move closer and closer to P, you can see that the secant lines, which are shown in colors here, they rotate around P, and in the limit you can see that the secant line will tend towards the tangent to the graph at P. So what is the tangent line? The tangent line is nothing but the limiting straight line PT towards which the successive secants tend. Okay. Now this then conceptualizes the concept of the tangent. But if you notice what I said in the beginning of the lecture, the derivative of a function at a point is the slope of the tangent to the curve at that point, right? So now we also have to understand what we mean by the slope of the tangent. But before that, let me also conceptualize what it means to move from successive points through successive points towards the point P. So if I'm moving from Q to R to S and so on successively towards P, Basically, the idea is, what do we mean? So if I ask you, what do we mean by saying as Q moves closer and closer to P, it basically means that I'm taking very small changes. Ultimately, I'm getting towards very small changes in X, and I'm talking of very teeny-weeny, infinitesimally small changes in X. And let's just formalize this a little bit. Let's give it a formal interpretation. So let's suppose my initial movement is from the point P to the point Q, which I'm now representing as follows. The point P is where X is equal to A, and the value of the function is f of A. And I move h units in the horizontal direction to point Q, which is to say QM units movement in the vertical direction. And the point Q's coordinates are A plus H. So X is equal to A plus H here at this point M. And the value of the function is f of A plus H. Okay. So if I draw the secant now, cutting through points P and Q, that you can see in this line in red. It's shown in this line here by the line secant line PQ. And when we say that as Q moves closer and closer to P, because in the limit it is a secant line which tends to the tangent line, we have that mathematically Q coming closer and closer to P would amount to H approaching 0, right? We have to get H to go to 0 if we want to talk of the tangent. Now coming back to the tangent line, because this is nothing but the secant line which tends to the tangent line as Q comes closer and closer to P. So now we are in a position to talk about the slope of this tangent line PT, which is nothing but our derivative. Okay, so what we'll do is we will start with the slope of the secant line only, and then take the slope of the secant line as h tends to 0, because that is what then gives us a tangent and therefore the slope of the tangent. Okay, so let's first look at the slope of the secant line PQ. That is going to be given by the vertical distance moved, which is QM divided by PM, and that is going to be the change in y upon change in x, which is f of a plus h minus f of a divided by h. Now this is actually a very important concept. It's reflecting this ratio f of a plus h minus f of a divided by h is reflecting what is known as the average rate of change, or the Newton quotient. It's averaging out, you're averaging out the movement over those h units that you have moved. So this is called the average rate of change. Now because in the limit the secant line tends towards a tangent PT to the graph at the point P, so the expression here for the slope of the tangent PT would be the limit of the Newton quotient, which is the slope of the secant line. So that would be the slope of the tangent would be reflected by the limiting value of the slope of the secant line, which is given by f of a plus h minus f of a divided by h. And when you take the limit as h tends to 0, that is the slope of the tangent to the curve at P, and that is nothing but our derivative, right? So the derivative, which is represented here by f prime at a, that is a limit as h tends to 0, because you're talking of an infinitesimally small change in x. So the limit as h tends to 0 of f of a plus h minus f of a divided by h. So it's a limit of the Newton quotient as h tends to 0. Now, because this definition revolves around a very an arbitrarily infinitesimally very small change in x, the derivative also represents what is known as the instantaneous rate of change. So the average rate of change is a ratio f of a plus h minus f of a divided by h, and the instantaneous rate of change is the limit of this particular quotient, Newton quotient, as h tends to 0. And as because this is a formula we'll be using this in this lecture as well, I had derived this formula in the previous lecture, which is lecture 22. F prime at a can alternatively be also written as the limit as x tends to a of f of x minus f of a divided by x minus a. Simply speaking, if I put a plus h equal to x here, so that would mean that h in the denominator would be equal to x minus a, and because h is tending to 0, x will tend to a. So that's how you get this particular formula. Now let's just look at some alternative notation that is also used for calculating the derivative. So in general, the derivative f prime of x is given by, if we don't take the point a in particular, but we just take the general derivative of a function f at the point at x. So f prime of x is the limit as h tends to 0 of f of x plus h minus f of x divided by h. Alternatively, we could also use the symbols y prime or dy by dx, which is read as the derivative of y with respect to x, or the derivative of the function f with respect to x. We can use this notation also. We can use this capital D notation, which represents it's just an operator. So it's an operation that you're performing on the function f, which we call the primitive function. So df of x is also a representative of the derivative of the function at x. Now, in economics, in physics, we also deal with a lot of functions which are functions of time. So, for example, if the variable y is a function of time, then we also use this notation y with a dot over it, which represents the derivative of y with respect to time. So, this dot notation specifically comes in when you're talking of the derivative with respect to time. And just some useful terminology before we move to the discussion on continuity and differentiability. The derivative of a function, as I said, in general is equal to the limit as h tends to 0 of f of x plus h minus f of x divided by h. And this is the derivative which we calculate if the limit exists, because as we'll just see in a bit that there may be certain functions for which the limit may not exist, the function may not be differentiable. So if the limit exists, we say that the function is differentiable at x, okay? And the process of finding the derivative of a function is called differentiation. So differentiation you can think of as an operation that you perform on the primitive function f, which transforms the primitive function f into this new function f prime. And this f prime is the derivative which we call the derived function, because it is derived from this operation that you perform on the primitive function f. Right, now this is something very important. Let's talk a little bit about these properties of continuity and differentiability and see how they're related to each other. And we're going to get some very important results here. So we have this first result here, that if a function f is differentiable at the point x equal to a, then the function is also continuous. It has to be necessarily continuous at x equal to a. So this is to say that differentiability, what we're trying to say here is that differentiability implies continuity. Okay. Now, to prove this, let us first get a sense of what it means for a function to be continuous at x equal to a. And we have done this in the lecture on continuity, that there are three conditions that must be met for a function to be continuous at x equal to a. One being the function should be defined at x equal to a. The second is that the limit of the function should exist. So the limit of f of x as x tends to a should exist. And the third condition is that the limiting value of the function, which is represented here on the slide as the limit of f of x as x tends to a, that should be equal to the value of the function at a. Okay. Now, this is what we have to prove, this condition, because if we have to prove continuity, that will be done via this condition. If this condition is fulfilled, then we can say the function is continuous at x equal to a. Now, what is our assumption? Our assumption is saying if, so we are using our principles of deductive reasoning. We have a function here which is differentiable at x equal to a. That assumption is given. Okay. So if the function is differentiable at x equal to a, we already know by definition of the derivative, that f prime at a is the limit of f of x minus f of a divided by x minus a as x tends to a. Okay, so if we use this definition, and in order to prove that differentiability implies continuity, so the function being differentiable means that this formula holds. Now consider the expression f of x minus f of a. Okay, this expression can be written as f of x minus f of a divided by x minus a, and I at the same time multiply with the expression x minus a. I haven't changed anything. I've basically just multiplied and divided by x minus a. I'm calling this equation 1, and if I take the limit on both sides of 1, on the left I'll have the limit of f of x minus f of a as x tends to a, and on the right I'll have the limit of x approaching a of f of x minus f of a divided by x minus a times x minus a. Now because f prime at a is this first expression for the limit, and because the limit of the product is the product of the limits, so this first limit, if I apply the limit to the first part of this expression on the right hand side, that will give me f prime at a, and that is then multiplied by the limit of x minus a as x tends to a, which you know is going to be 0, right? So we now have that the limit of f of x minus f of a as x tends to a is equal to 0. And this I can just algebraically manipulate it. I can take f of a to the right hand side to get the limit of f of x as x tends to a equal to f of a, and this then is exactly the condition we wanted to prove that the function is continuous at x equal to a. So the result that we have here is a very crucial one, that differentiability implies continuity. Now if we just use our principles of logic, and if you are not able to recall those principles, the necessary and sufficient conditions bit, you can go back to the lecture on logic, which is available on YouTube. So here, because if a function is differentiable at x equal to a, it necessarily implies that the function is continuous at x equal to a. So continuity is a necessary condition for differentiability. It is not a sufficient condition, it is a necessary condition for differentiability, and we can actually turn things around. So if we are saying it's not a sufficient condition, this is basically to say, this is basically where, we are asking the question, are all continuous functions differentiable? And here we are going to show that the converse of this statement is not true. So differentiability implies continuity. If a function is differentiable, then it is necessarily continuous, but the converse is not true. And this is something we're going to demonstrate with a counter example. And here I can just give you an initial taste flavor of things. Here you have this function shown by the graph here in the curve here in white, and this function you can see is continuous at x equal to a, right? There are no breaks in the graph. The limit here is going to be as x tends to a from either side. The limit is f of a, and that is the value of the function here. So just visually speaking, we're saying here that we can easily see here that there are no breaks in the graph, so the function is continuous at x equal to a. But the problem here is that the graph does not have a unique tangent at x equal to a. If you see here, if we think of the tangent as the limit to which the tangent line is the limit to which the secant tends, then here the secant does not take a limiting position, because if I approach this point x equal to a from the right, then I get this kind of a tangent here, and if I approach x equal to a from the left, then this tangent is given by this dashed line here, which I'm trying to, if you can see the movement of the mouse here. So this is the case where the graph will not have a unique tangent, and here, if we take the right derivative and the left derivative, the right derivative here is the limit of f of x minus f of a divided by x minus a as x approaches a from values to the right of A. So if the right derivative here is alpha and the left derivative f prime as x approaches A from the left is beta, then basically what we are seeing here is that the left side derivative is not going to be equal to the right side derivative. Alpha is not equal to beta, even though the function is continuous at A. And here, if you notice, visually this means that the graph has a kink or a corner at x equal to A. So if you notice here, there's a sharp point also. You can some people call it a sharp point. So there's a sharp point here. There's a kink or a corner at x equal to A. This is where we say the function is not smooth. Okay, so you can smooth out the corner if alpha were equal to beta. That could have been the case only if alpha were equal to beta, that is the left side derivative, were equal to the right side derivative. So with this we conclude the first part of the lecture, and we will continue with this discussion in the second part. Thank you.